Now let's move to the next fundamental part of ODA's complete interoperability mission, an interrelated set of BIM technologies. Last year, we shipped out IFC SDK, the industry's first professional and affordable solution for IFC. It has been rapidly adopted by member companies and is widely used for data access, geometry processing, and high-quality visualization. IFC is just one piece of Open BIM puzzle. This year, we've added advanced validation and collaboration tools to our BIM offering. This includes a new validation engine, support for MVD, BCF with both XML and REST APIs, and the newly developed IDS standard. Our support for Open BIM standards from BSI, together with support for Revit and Navisworks file, and architecture, civil, and map extensions for DWG, give ODA a unique offering within BIM industry. The implementation of our IFC SDK is closely related to the implementation of ISO 10033 standard, well known as STEP. So we've introduced several ISO-compatible features in our SDK. These include the ability to compare application instances, delete from a model, near copy of instances in the same model, a simplified early bound API for users who want to have additional checking on the compiler, and the ability to get attribute type names in camel case as they exist in Express scheme. Starting this year, IFC SDK also includes a powerful new Express interpreter implemented according to ISO 10033 standard part 11 without any dependencies on third-party technologies. The new interpreter provides complex functionality such as Express schema runtime initialization, derived attributes, and where rules evaluation.
The main parts of Express Interpreter are parser, which takes an exp file as input and creates abstract syntax trees for expressions, semantic analyzer, which checks variables and types and fills Express schema metadata, and interpreter, which evaluates derived attributes and where rules using late-bound access to attribute values. The interpreter can be used with any Express-based format. It has been tested with several STEP and CIS2 schemas. In addition, it's used for IFC. We'll be making some additional improvements to the interpreter during the coming months, but the current version is ready for production use. This is a short demonstration of the Express Interpreter in action. The run shows the evaluation of the most complicated derived attribute P of IFC axis 2 placement 3D. The Express function IFC build access returns evaluated coordinate system as an array of vectors. The evaluation is complicated by the fact that the function itself has several nested function calls, so the full Express source code is quite complex and can be seen here. Let's prepare input data, the x-axis with following coordinates and z-axis. Notice that z-axis isn't normalized. Now let's call the evaluation and return the result into an aggregate. Everything passed OK, and let's print the result vectors on the screen. X-axis is the same as input. Z-axis is normalized now, and y-axis was calculated by the function IFC cross product. Read-write support for ifcXML 2x3 has been available in ODA IFC SDK since version 22.6. Here's an ifcXML read-write demo. Let's open a simple IFC file. The file size is about 17 megabytes, and we'll export it to ifcXML. ifcXML file size is usually 5 times larger than the size of the source IFC file, so we've just created a file that's about 90 megabytes. Then let's reopen it, and you can see absolutely the same geometry, attribute values, spatial structure, and so on. Based on members' requests, we also added support for legacy IFC schemas, such as IFC2X final and IFC2X2 final, so old files can be produced by IFC SDK. In addition, building smart company in collaboration with domain specialists and software vendors, is going to introduce new IFC 4.3 standard, which supports formalization for rail and road related areas. The work on IFC 4.3 is still in progress, but the result of our collaboration with Building Smart Rail Group is an early implementation of IFC 4.3 release candidate 4 supported by IFC SDK. The recent release candidate is more or less stable and introduces railroad specific entities and new classes for geometrical representations of alignments using several new curves and geometrical segments.
Several IFC 4x3 files with alignment, semantic, and geometric views were produced by ODA example applications that convert land XML and XTR alignment data to IFC during ODA participation in the new schema unit testing period. These applications can be found in example section of IFC SDK. And now, let's look at a short demonstration of IFC 4x3 geometrical abilities in OpenIFC Viewer using one of these files. Alignment can contain different types of segments, which describe configuration for lower parts independently from each other and construct resultant alignment curve on the final stage of visualization. Each segment trims underlying base curve that uses simple primitives such as IFC line and IFC circle, or new complex curves such as IFC clothoid or other IFC spiral subtypes. These new types of curves are mainly used in road and rail design. We also implemented support for several geometrical entities as IFC CSG primitives for the special ASYS modeler and IFC triangulated irregular network, which is typically used for terrain representations in recent IFC schemas. We implemented a new sweep operation for the ODA facet modeler. So Facet Modeler now supports the full set of modeling operations required for IFC. Material support was significantly revised several versions ago to reduce the amount of materials created during vectorization.
Created by one of the founding members of the CAD Alliance Group, one of the main distributors of Autodesk products in the 2000s. Its core business, computer-aided design. 20 years in the realization of applications and automation of CAD plans. A flagship product, SciView, independent software that does not require any other CAD software and allows you to integrate CAD solutions into your developments. Web Infinity is know-how in development, experience of more than 20 years in the realization of applications for our customers, knowledge of standard languages, knowledge of standard databases. The main customers of Web Infinity are SNCF, Solitange Bachi, and Solitange Freisenet from the Vinci Group, Antargaz, Hammond, Smartcast, etc. At the request of our customers, we have integrated the import of IFC files in order to integrate them into their DWG format on their project. SciView using ODA libraries will allow you to open an IFC file in order to transform it into a DWG or DXF file to be able to integrate it into your projects. You can set SciView to import IFC entities, either as a block or not, by exploding them into layers and giving the names of the layers the names of the IFC entity groups. To open an IFC file, nothing could be simpler. You do the open function, then you choose the type of file you want to open, in our case, IFC. You choose your file, and the IFC entities will then be transformed into AutoCAD entities according to your configuration, blocks or polymesh. Each identity will be distributed in a set of layers. You can then manipulate this file, zoom, change shading mode. You can also change from ISO mode to perspective mode. Each IFC entity will be created according to your configuration, either in block or in polymesh. The name of the block being the name of the IFC entity they are placed in. layers being the name of the group of the entity always following the request for the configuration. A set of layers will be created per IFC entity group, and you can manipulate these layers, freeze them, and unfreeze them at will. You can then save your project in AutoCAD DWG or DXF format in the version you want. You can then open this DWG file either with AutoCAD or with AutoCAD Clone and manipulate it in the same way and use it directly in your drawings. Entities are kept block or polymesh and all layers are preserved. Opening an IFC file and importing in DWG format will allow reading BIM formats from Revit or any other software in order to transform them into AutoCAD format, and then integrate them into other applications such as a railway tunnel plan. Here, carried out for the Greater Paris project, and to use it in another application such as this one, which allows to undo the compensation boreholes for the company Soltanche Baci.
Merci.
So in March 2020, Building Smart International published the technical roadmap, and that had kind of a forward-looking approach to standard solutions, technical services. It looked at modernization and normalization of IFC, also at the future of API standards like BCF. How IFC and the BSD would be more integrated. And it also noticed a missing piece of the puzzle, and that was this more dynamic way to define your exchange requirements. ISO 19650 calls this the exchange information requirements. So really defining what do I need in my project, where do I need it in an IFC file, what kind of properties need to be linked, what are maybe even the allowed values of those properties.
If there was a standard that we could just straight read in and check against that in Solibri, that would be good, and also like it would build more confidence in the projects.
Heijmans is one of the main contractors in the Netherlands. So in my specific business units, we do about 120 projects every year, and just on a daily basis, we've got about 15 BIM managers that are checking models, basically based on the model quality Pasi was mentioning before. And in the Netherlands, in the past sort of 5 years, we've seen a real uptake on main contractors like Heijmans, but also fabricators and also advisors specifying information needs. But they tend to always do it in the Excel format or PDF format. So basically formats that are human readable. And this IDS project would really enable us to to then map that human readable format into a computer readable format. And then if the likes of the modeling tools, for example Autodesk Revit, and then the checking tools, for example the likes of Solibri, would implement this IDS standard, that would basically enable our BIM managers to do the model checking a lot faster, and I guess with a better quality in the end as well. So it would save them a lot of time. So that's the main interest of Heijmans is basically to speed up that process on being able to, on one hand, distribute good quality models to our subcontractors, but on the other hand also check the model files that we are being given by advisors from the likes of architects or engineers, etc. in the process.
Yeah, I think the most generic common problems is that I have an information requirement, I have an exchange requirement, I want to define that. My walls need to be using some kind of a local additional classification system. Could be co-class, could be NLSFB, could be uni-class, omni-class. And I also want the additional properties. Are the walls load bearing? Are they outer walls, inner walls? And they also need that to be consistent with each other. So those kind of information requirements are quite logical, and those are the typical requirements that the IDS can facilitate.
Well, one of the comments from one of the people who offers online Revit training on Facebook was that he was quite happy to use, based on Revit, quite happy to use IFCs and so on for export, but he was of the opinion that if you actually wanted to save the detailed information, you actually had to type it into the notes that would be passed across, because the IFC model as it is isn't fine-grained enough to actually capture a lot of the requirements of the people developing the models. So if we have to have that workaround within the IFC model, we need a capability, a robust capability that allows easy extension by people on a one-on-one basis, but exchanging from one to another. And I'm hoping that the IDS is I'm going to expect that the IDS is actually a good solution to that problem.
IDS is it's not seen as such at this moment, but from my perspective, from a Building Smart perspective, IDS is also a bit of a missing link in this full open BIM workflows.
Yeah, basically, and I think also that we should ensure that like the user workflows, say starting from specifying the requirements and then entering the BIM data in the authoring tools, and then like checking the data, that they all are fluent, so that this wouldn't be another hurdle, but instead of making things much more smooth than they are at the moment.
The current status of the IDS project is that we've rounded up phase 1. We've done a first implementation. I think the latest version is on version 0.4, which is all available on GitHub. And I think this 0.4 version is a really good version to start the next phase 2, which will be more about basically getting the software vendors involved, do implementations, and I guess do testing afterwards. Obviously, we're very eager to, just like I mentioned, I guess in the kickoff meeting of the IDS project, to get a few more buttons inside of the software that we use on a daily basis. To be able to, when you do an export from the likes of, for example, Revit, that, the IC export that you're producing is actually as per the IDS file that you've imported into the software. And once we start checking the IFC file in the likes of Solibri, there will be a button where we can just import the IDS standard as well, and just basically say check against this IDS, and it takes a few minutes, and then we get a nice report. So I'm very eager to get those buttons into the software.
Not limited to members. Everyone is free to join. Just please come in and help us validate this and start implementing it. You're very welcome to join.
This great discussion about IDS highlights the point that IFC is always exported according to some type of requirement. IFC has been around for decades now, and many different toolkits and applications have produced millions of IFC files. Unfortunately, though, many of these files contain errors. During the development of our IFC SDK, we encountered a significant number of IFC files with errors of varying complexity, from basic syntax errors to topological errors with incorrect relationships between objects. The most basic thing that we can do for the industry is to provide tools that can report such errors. In some cases, it's possible to make implicit fixes, like transformation of non-instantiable objects into building element proxies. So an error logger is the lowest level of IFC SDK's new validation engine. The next level is SDAI validation, a set of predefined interpretable or WHERE rules and non-interpretable validations that includes validation of string width correctness, validation of relationships between objects according to schema, and so on. This level is performed by the appropriate C++ API, SDAI calls described in ISO 10303, and will be available for all ODA-supported Express-based formats going forward, including the STEP format family. And the highest level of validation available in IFC SDK is format-dependent verifications. These include implemented collections of validations on the IFC level, forthcoming MVD, model view definition validation, which is in progress now, and validation according to the new IDS requirements, which are currently being developed by BSI. From the API point of view, the validator class runs through a set of appended validation tasks for model instances, collects the result of validations, and notifies a set of predefined notifiers that print the results on the screen, to a text or HTML file, or a user interface window. Optionally, validation task implementations may have a healer protocol extension attached, as shown in the following demo. This demo shows loading a file with and without validation and healing. The file was opened with validate and heal turned off, and it has a significant error. It doesn't have a plane angle unit assigned to the IFC project. That's why we have a lot of gaps in the visualization. It has incorrectly drawn some circular-based elements, such as walls and parts of roofs. Now I'm going to reopen the file with validate and heal turned on. The healing heuristics determine that the file doesn't have plane angle units assigned to the IFC project. It analyzes the attributes of angle types to see if they're defined using radians or degrees, then creates an IFC SI unit instance and assigns it to the IFC project. As a result, we now have totally correct geometry for walls, roofs, and other parts. The model validation process can be resource intensive, so it's impractical to run all validations every time an IFC file is loaded. Such an approach makes sense and can be done for relatively fast validation tasks on the IFC format dependent level. For the more complex task of whole model validation on different levels, we've added a validation tool to Open IFC Viewer. It allows the user to select the desired set of validation tasks. Here you can see a set of predefined SDAI validation tasks and a set of loaded IFC level validation tasks that we'll use to check the model. Let's check them all and click Validate. After a few seconds, we have the result: a list of instances and their attributes, or where rules, that have not passed the validation checks. The list of results can be saved as HTML or text, and the table can be updated by applying different data filters. There is another experimental validation plugin for Open IFC Viewer we'd like to mention here: validation according to IDS rules. The IDS standard is new and still under development by BSI, but ODA has developed an early IDS validation prototype as an implementation of the validation task interface for our validation engine. Here is a dynamically created set of IDS validation tasks in the subtree for a selection, where each task has a loaded IDS file containing validation rules. The collection of these IDS files is placed in a predefined folder on disk. Let's select the validations we're interested in and click Validate. The validation is done quickly, and the results are displayed in a standard manner for further investigation. Another useful new feature available in recent IFC SDK versions is a customizable event logger, which can be accessed from the C++ API or SDAI. The logger is typically used for logging file loading errors, including syntax errors, non-instantiable or unknown entities in the file, and for geometry compose events logging. The logger may be used by customers for any logging related purposes. It's turned off by default and can be turned on by an appropriate call to the SDAI session instance. In Open IFC Viewer, the event logger results are shown in a separate window, which is optionally open just after file loading and geometry visualization.
Several new features were added to BIM Collaboration Format API, which is a part of IFC SDK. Such features are related to comments and topics management, as creation, editing, and deleting. Updated BCF project can be saved into BCF zip file. Many of ifcXML API features are used to implement OpenIFC Viewer's BCF Manager palette. Let's perform a single IFC file review using this feature. It's needed to create a new BCF project and add 3 topics. The first mode of the tool adds selected objects on snapshot. The second adds selected objects with highlightings. And the third mode finds intersections with initial entity and creates snapshot with all intersected objects. Let's save our project and open it in third-party BCF viewer. We will add some comments here and save changes into the same file. Now let's reopen it in BCF Manager palette and read comments we've just added. One topic has become unnecessary, so it has to be deleted.
In the field of construction and design, it is becoming difficult to work without BIM models, which allow you to more efficiently plan, design, and build. Cloud BIM solutions provide the more efficient way to organize communication between all project participants, and it solves the problem of single source of truth. But mostly all cloud BIM solutions work with the IFC file format or their own internal file format. And to start to work with such solutions, you need to have an appropriate software to convert your file to an appropriate file format. And only then you will be able to upload your file. OpenCloud provides multi-format file handling, which means that you can use any device to upload your files. And then you can use any modern browser to visualize your file in the browser or getting analytical information. And this is only a part of functionality that OpenCloud offers. OpenCloud Server provides collaboration functionality as well. For joint work of several users, they can be assigned on the project by the project owner or the administrator. And then users will be able to create issues, create reports, leave comments, and do other operations as well. Also, the administrator or the project owner can assign specific settings for this user on this project. If you need, you can make your project public. To do this, you need to change project settings. OpenCloud Server supports BCF REST API, which is a part of the OpenCDE specification that is well accepted in the BIM industry. With the Server API, you can work with such entities like projects, topics, events, and others. For user authentication, we have supported the OAuth 2.0 protocol, which is a part of the BCF2. Tools compatible with the BCF REST API can work with the OpenCloud solution mostly without any problems.
And some words about our future plans. On the IFC side, there will be some significant SDI improvements as our new IFC runtime implementation gives the ability to work with Express-based formats such as IFC or STEP without generated classes. So data can be accessed just after loading and processing of EXP files. Generated early bound classes, however, will still be available for those who prefer this way of working with data. We are going to continue our work on Express interpreter optimization and on implementation of new features based on the interpreter. Also, we are going to extend our collaboration support with the recent BCF3 format in conjunction with our participation in BSI OpenCDE initiative. Our nearest plans include visualization support for new entities in forthcoming IFC 4.3 format. MVD XML support for validation is still under development, and it's going to be shipped out as production in a few months. And of course, we will continue to support development of the new IDS format and its implementation as part of ODA IFC SDK.
BIM-RV is ODA's standalone toolkit for the import, visualization, and creation of Revit models. BIM-RV is an active development product for ongoing being done for updating public API for providing more extensive support element creation and editing. BIM-RV now can load in the latest file format 2022. The public API was enhanced for possibility to provide full access to data in the latest file format. Older files from version 2015 onwards are automatically updated to the latest version during loading, giving clients' applications possibility to give consistent access to the data regardless underlying file version. BIM-RV also can write files in 2022 format. File reading and visualization are in production state. I want to show visualization for several files. We draw all elements with geometry. BIM-RV supports materials that can contain data for different visual styles like fill patterns, textures, colors, and so on. On the screen you can see an example of a complex model with a set of buildings. This is an example of a shaded visual style. And another example of complex file in realistic visual style. We also can draw sections. Section geometry is not stored inside file, and BIM-RV generates this geometry on the fly. You also can see annotation elements. And one more example, sections, several sections on the screen. Elements have parameters. They are not stored in the file. Each element collects them by its hierarchy. You can get list of parameters and get value for each of them. We can select one element and see its parameters. They can be grouped by area or alphabetically. You also can see their built-in representation. Next, I want to show the latest enhancement in BIM-RV visualization. First is visualization of disciplines. BIM-RV has a discipline parameter, but element doesn't have such settings in the file. To support this functionality, we research and added such functionality to the categories. We also changed the visualization process for the ability to move active category to the first plane and draw other elements with another visual style. The result you can see on the screen. Visualization of schedules. Schedules normally doesn't contain data inside files. They have only rules on settings for collecting this data from elements. We implemented initial version for collecting this data for schedules by elements. It supported formatting, grouping, and selecting data, and we continue working on more complex cases for support full functionality of schedules in the product. Decol element visualization was implemented a year ago, but this year we added advanced functionality for this element. First, we supported clipping for decol element, and also we supported a case when a part of decol element are placed outside of the host element. In this case, we mustn't draw the part of the decol which stored outside of host element. And the result you can see on the screen. Next very important area is possibility to edit or create elements in Revit files. This functionality is still under development, but we can create a set of elements. This is curve elements. It can contain different lines, arcs, and so on. materials, different views, custom parameters, direct shape, and free form elements. We completed work on form elements and their void forms. This is base element for creation family geometry. They contain BREP geometry inside. We also can create family geom combination. This is Boolean operation on form elements in family database. And we also can create openings and host elements inside family database. We are working on interactive creation and editing of forms elements. In this case, the element must be put into edit mode, which will change element to the sketch. The customers create a sketch. When editing is finished, the sketch will be verified by ODA constraint solver, and if the data is correct, it will be used to create the element. Currently, we can create all forms elements this way, or convert solid form to the void. We continue working on editing in this mode. We continue actively works on family import. We can import family database and create internal database. Create family symbols. We can activate family symbols, but this works only for active family type. Family has geometry only for active family type internal, and we use this geometry for creation geometry in the symbol. We can create family instances for activated family symbols. We also must modify geometry of host element for hosted family instances, and this already works. We continued working on recalculating family geometry by family types. A family contains geometry only for active family type. We implemented the initial version of rebuild geometry by type. Recalculation of the family geometry requires constraint solver. The solver is used to update and verify sketches of forms, modification dimensions, and ref planes. If the verification passed, then the geometry of the form can be recreated. So we need to update geometry of all forms in the family and perform Boolean operations on them. We can change family type, update geometry, and save the file. Then we import the family into a model as a new family and activate the symbol for the active family type. After that, we can use this symbol for creating different family instances. So, for example, we can create windows with different sizes. We can recalculate geometry of a family for existing types, but we continue to develop our constraint solvers for the ability to verify and create new dependencies on the sketch. We need this for the ability to modify and create new family types. We can recalculate geometry in the family database, but we are working on the ability to do this in the model. This will provide the ability to activate all family symbols in imported families, and as a result, we will be able to import families with several types, activate all family symbols, and create family instances for any of them. IFC export for Revit file. You can see the example on the screen. We open the model of a library in ODA BIM application, visualize it, and call IFC export. Currently, the export supports the IFC 2x3 version. We will open the resultant IFC file in Open IFC Viewer and look at the result. We implemented export of project information, measurements units, building, construction site, collection, and translating levels for IFC. We can convert all geometries of elements and materials. For each element, we get visible geometry by settings, translate it, and modify. We have to modify it because geometry representation is different in two file formats. Most of 3D geometries in Revit are BREP geometry, but for IFC 2x3, we need to create meshes. In other cases, we need to create data and settings for building the geometry during interpretation of IFC file. Each case should be researched and implemented in the export. We implemented the ability to save Revit parameters as properties. Also, we implemented several IFC property set, and we continue work on this functionality. The example property set you can see on the screen.
Another set of ODA SDKs for BIM workflows includes vertical extensions for DWG to work with architecture design and drafting, civil infrastructure design, and GIS data. Architecture SDK contains all the architecture primitives such as walls, doors, windows, and more. In addition, it supports construction documentation workflows through associative dimensions and schedule tables and other classes. Architecture SDK is a mature product constantly improved. This year's focus was improving the stability of stairs and railings. But architecture objects do not exist in isolation. To design a house, you need land survey, earthworks, as well as pipes, roads, and other infrastructure objects. ODA Civil SDK is designed to handle these areas. Currently, Civil SDK contains models to work with cargo points, alignments and surfaces, pipe networks and structures, corridors and assemblies, catchment areas, and others. ODA Civil SDK supports object versions from 2006 to 2022 and visualization for all objects. Creation is implemented for cargo points, thin and grid surfaces, alignments, profiles, and profile views. This year's focus was in two main directions: roadway design improvements and surface enhancements. Roadway design improvements include 14 new transition curves implemented, please see the table, alignment, masking support, now a part of the entity may be hidden, and get nearest station algorithm rework that allowed to provide additional accuracy. Surface enhancements are improvements to triangulation engine that decrease the creation time for a 100,000 point surface from hours to seconds. Contour smoothing support that significantly improved the appearance of triangulated surfaces. In addition, a sort of improvements for visualization and format support were done. Our map project allows CAD and GIS data to work together in one application. ODA Map SDK connects to an GIS database, SDF, SHP, etc., and imports GIS data into a DWG file in a DWG representation as DB entities. Similarly, DWG data can be converted and appended to a GIS database. This year, we introduced several new features and improvements to Map SDK, such as map cage support, modification of map entity geometry data, and map import command. Map cage support allows ODA to reference directly a GWS file, a file that is created when changes to a GIS database are made but not committed. For example, if changes are made to a map layer, a copy of the database, a GWS file, is created and this copy is visualized instead of the original database. Thus, map cage feature allows the support of GIS objects graphics data modification. This example shows the entity geometry modification. After the preliminary actions, we're able to zoom to extents and dragging to see our layer, the roads layer of the New York City. Zooming closer, we see that one of the roads does not fit the background map. Let's fix it. Simply select the road and drag it by its grip points. Please note that this road is a temporary map feature object, which are commonly inherited from simple DB objects. Therefore, grip points of the base class may be used. The map feature object has functions to synchronize its geometry data with GIS database. One more improvement involves 3D layer visualization. As you see, initially, the layer was visualized in 2D, but we can switch to a 3D mode. The new map import command inputs the GIS database data into a DWG representation, such as ODDBM polygon, ODDB polyline, etc. Currently, it can connect to SDF, SHP, WFS, SQLite, Postgre, and MySQL databases. The input is not limited to simple geometry only. Complex data may be inputted as well. In this example, you see a map input command. Select the connection type to SHP and select the SHP source file. Next, determine the GIS layer, and after additional input options, we see the result. As you see, all the three DWG extensions, architecture, civil, map, taken together allow us to make a step in the direction of CIM, City Information Modeling, that attempts to solve the challenges faced nowadays by large and modern cities.
The CAD Professional drawing and modelling system has changed over the years and is now built around the Open Design Alliance libraries and makes extensive use of the Drawings SDK and the Architecture SDK. As founder members, we have access to the source code and, equally importantly, a two-way, good working relationship with the ODA teams. The move to the ODA libraries has immediately been of great benefit to our clients. They can interchange drawings fluently with other professionals, and they now have the ability to design in 2D or 3D as they require. Furthermore, by keeping up to date with our latest versions, they automatically have access to many of the new object types which each newer version of DWG supports. The markets in which we are operating are changing fast. It's not that long ago that users were content to create two-dimensional plans and elevations, but that changed to needing three-dimensional models, and they still demand more. In the current architectural environment, there's a need to combine data from multiple sources and utilise that data to optimise any given development to the location, environment and population within which it is to be sited. This is where our latest addition, CAD-GIS, comes into its own. CAD-GIS enables users to identify the present and future needs of any location by enabling the representation of information gained from a wide range of sources in a single, coherent CAD document. The information gleaned can not only allow the designer to make decisions based on current data, but also to see and utilise future trends. Examples of the information the use of CAD-GIS can yield include identifying local needs based on availability of similar resources or facilities within the area, identifying prime locations for the siting of a development, including land and property values and ownership, analysing population demographics and comparing to available resources, identifying previous planning applications made for a particular location, providing information of possible chances of success or rejection, information on transport links, be they rail, road or public transport, and highlighting problem locations such as accident blight spots, congestion, parking availability and restrictions, low emission zones, access charging, tree protection zones, flood risks and many more. All of this can now be done in CAD, with the results combined with the model and construction data itself. So utilising the power of the ODA SDKs has enabled our team to concentrate on the vertical applications, evolving CAD from its simple origins as a two-dimensional drafting system to a powerful hybrid solution combining the best of drawing, modelling and GIS.
Few words about Autodesk Navisworks files formats. These formats integrates various projects from various implementers in various files formats into one file. It allows us to use a whole picture and analyze these projects together. There are three main file formats: NWD, NWF and NWC. NWD is a file format that contains all the inputted files inside itself. NWF doesn't contain inputted files inside itself, but just contains references and transformation matrices inside. Also, when Navisworks imports files, it creates cache files named NWC. Files can contain such information as clash collision test and results, annotation to mark interesting places, sectioning, and so on. Also, it can contain data like animation or planning. We expanded API for access to model items data like properties, model units, and flags. The next step, I would like to tell you about the enhancements that we were able to achieve in our plugin for Visualize. Here you can see the old version of AutoVisualize Viewer on the left side and the newest one on the right side. We added an automatic settings of the texture folder from the registry for Windows platform. In early versions, it was needed to copy texture directory into directory with Visualize Viewer. We improved overall stability and performance of models visualization. To improve hidden objects detection, we had to implement the reading of shadow override element stream. Now BIM SDK has access to this data. Nodes from model's logical hierarchy with layer type are now added to Visualize database like TV layer objects. All the visual styles are now supported. One small hint. NV to Visualize plugin has example how to check if model node is inside of Clipbox. I would also like to add a few words about improving the rendering of Navisworks models using tools from ODA SDK. Let's open an NWD file with our new MFC-based application. We can see that the object tree was loaded. Visualize it. The model was rendered. We are able to zoom and rotate the model. Here we can see new materials and textures. If we select an item on the tree, the corresponding graphical representation will be selected and zoomed in. For example, floors and levels. We added support of visual styles, realistic shaded view without texture, hidden line and wireframe. Now, while rendering, the node's hidden flag value is also taken into account. The model can be zoomed to extents, zoomed to selected items. Users can also choose a vectorization device. Now we changed it to OpenGL. We also improved material settings to support bump and opacity textures. Here you can see 3 screenshots: simple texture without bump texture, and full texture. We added support of tube geometry while GIGS rendering. Also, we implemented styled text rendering in Visualize. One of the largest parts of our work last year was to start writing correct NWD files. We started this task with resaving NWD files, which were opened with BIM SDK. In the scope of this task, BIM team implemented saving of streams like lights elements, spatial hierarchy, and shadow override elements. Saved NWD files won't be correct without these streams. A lot of time was spent investigating and implementing spatial hierarchy tree generating. The next step was to create an empty database and add methods to fill it. BIM users can add new nodes to hierarchy tree and geometry data to model items. It's possible to apply transformation matrices and materials. Added possibility to set viewpoints data like camera settings. To demonstrate the possibility of creating new NWD files in the BIM SDK, we created a console application, Create Dummy NWDXM. This demo application can serve as an example of how to create a new NWD file from scratch by adding new hierarchy, geometry primitives, and set up camera. Here we ran the demo application and got a new NWD file as the output. This file contains several model items with geometry like shells and circles. It also shows how to apply textures to objects. After file creation, we can open it in Visualize Viewer or Navisworks and check the correctness of object hierarchy, geometry, and textures. The source code of this demo application is available for customers. This year has not ended yet, so we are going to decrease the memory consumption BIM SDK takes while working with huge files. We've already started the implementation of grids and levels classes. BIM SDK users can try this API for this data. Selection sets streams also started to be parsed due to the plans for this year, and we are going to finish the implementation by the end of this year. I hope we will have time to implement animation stream parsing and provide API for working with these classes in release 22.12. Let's open Revit's RVT file with AutoVisualize Viewer. It takes for a while. Here we can see the 3D view and the hierarchy of imported RVT file to Visualize database. From the main menu, we are able to export Visualize database to various formats. Let's export it to NWD file format. The export has finished, and now we can open the result in the same AutoVisualize viewer. We can see the file has been exported well. Let's check this file in Navisworks. As we can see, Navisworks successfully opened our file. If we take a look to the left panel, we can observe the same objects hierarchy like in Visualize database. Materials and textures were exported as well.
Growing renovation activity and increased demand for digital twins have the point cloud topic more popular in recent years. The main advantage of point clouds is obtaining accurate model of real objects, which is in demand in both CAD and BIM. ODA began working with point clouds to provide interoperability for the recap point cloud data that can be embedded in a DWG file. After several years of development, we now have an advanced point cloud engine that is tightly integrated with other ODA products and can be used to process various point cloud formats. ODA provides a set of tools to process point clouds. The tools are designed to solve the following tasks: read RCS and RCP point cloud formats, convert unstructured formats like PTS or XYZ to structured RCS file, and also visualize point clouds. The main supported point cloud format is RCS. The format is the core of our point cloud engine. During visualization, our engine checks the visibility of the point cloud in the current viewport and selects the appropriate level of detail. This approach allows you to efficiently read large point cloud projects. For example, the following project is a model of a building containing about 12 billion points and occupying about 60 gigabytes of disk space. One of the latest innovations in our toolset is on-the-fly conversion of unstructured point cloud during visualization. For example, if you open a PTS file in ODA Viewer, your PTS file will be converted to a structured RCS file and efficiently rendered using our base engine. ODA Viewer will similarly import and convert the XYZ point cloud format, which has no strict description, so it's not a simple task to process all data cases automatically for this format. Our sample application contains an additional dialog, which allows the user to guide the conversion process.